ones you guys learned, HCl, HBr, is it going to go to the more or less substituted position? More. Nice. So it's going to look like this. Okay, and then it's asking, is this product achiral, a mixture of diastereomers, a meso compound, or a racemate? Well, for something to be chiral, it has to have 4 different stereocenters, right? It has to have 4 different things attached to the carbon. If we check this carbon, we have this different chlorine, right? And we have this different CH3. But are these 2 carbons different at all? No, right? So it's going to be achiral. It doesn't have any kind of stereochemistry at all. Does that make sense? Any questions? Okay. All right, so how many stereocenters, aka chiral centers, are present in this molecule? So we're going to start at this carbon. I have 2 CH3s. So already I have 2 of the same thing, right? That can't be a stereocenter. So we'll move on. This carbon has a chlorine, has a hydrogen. It has this carbon over here, which is in a different chemical environment than this carbon over here, right? Both those carbons have different things next to it. So that's a stereocenter. Then I have this carbon right here, which also has a hydrogen. It has these carbons, this carbon, and this carbon, which are all in different places, right? They all have different things going on in their lives, all different. So that's going to count as another stereocenter. And then actually, we have this carbon right here, which has this H attached to it. It has this CH3 attached to it. I know they wrote it like that to kind of trick you up. It has this carbon over here attached to it, and it has an O attached to it. So it also has 4 different things going on. So that's going to be your 3rd stereocenter, is that carbon right there. So that's why the answer for this one is B. Do you guys have any questions on this question? I think it was an easy concept. I think this one little carbon was a little tricky in how they placed it. But, you know, just be careful. Okay. All right, so we're going to do nucleophilic substitution and elimination now. So which alkyl halide would you expect to undergo an SN1 hydrolysis most rapidly? So SN1, right? What is that? Is that 1 or 2 steps? 2 steps, right? It's the opposite of what you would think. SN1 has 2 steps. So it's not based on steric hindrance, right? It's based on the stability of your carbocation because it's alone for 1 whole step. So you want a stable carbocation. So you want the one that's going to give you the tertiary carbocation, right? You also want a good leaving group. So which one of these is the better leaving group out of bromine, chlorine, iodine, and fluorine? Do we know? It's not chlorine. Iodine, right? I think it's as you go down the periodic table, if I'm not mistaken. Yeah, as you go down the periodic table, there are better leaving groups. And you are given a periodic table on the ACS. So if all else fails, flip really quick, pick the one that's furthest down. That's the best leaving group. Any questions? Okay, what would you expect the major product of this reaction shown? So we have NaOCH3. We usually see it as Naomi, right? It's the same thing, methyl. What is that going to do to a Br? That, you're thinking Orgo 2. This is more of an Orgo 1 question. Yeah, that's the trickiness with this test.
Is it the one that can attack from the back?
It's actually just going to eliminate it, right? When you use Naomi on a Br, you get the elimination product. These 2 together.
Oh, I think I was thinking about SN2.
SN2? This is a elimination addition, or elimination reaction. So do you guys think it's going to go Markovnikov or anti-Markovnikov? Markovnikov, right? It's the Naomi is the basic one. Usually the basic ones go Markovnikov, like adding water, which H3O plus goes Markovnikov. It's the weird ones that they specialize to go anti-Markovnikov. So this one's going to give you Markovnikov. So it's going to give you the more substituted double bond. Right? So we can just cross this one out immediately, right? Because that one's not going more substituted. And then between these three, first of all, how would you even get this double bond, right? How am I going to eliminate my Br and it comes out all the way over there? That doesn't make sense. Now, typically, both of these products would be equivalent. But because you have a benzene ring right here, this one can actually resonate throughout the entire benzene ring. And again, resonance more stable, so B is going to be your answer. That's going to be the major product of your reaction. I don't know if it was E1 or E2. I don't remember those. I recommend looking at the charts before the exam, but I don't remember. Any other questions on this one? Yes?
How do you tell if it's orgo 1 or orgo 2?
Yeah, that's a tough question. A lot of times you start doing orgo 2 things with what's orgo 1 and orgo 1 with what's orgo 2. I just recommend, flipping through the books. Maybe look at the review. Clearly you can't read the whole book before the exam, but you can maybe look at the review sections in the book. The first half of the book's orgo 1, the first half of the book's orgo 2. Look at I'm thinking about the Klein book, but everybody has access to it if you go to the SARG lab. Look at those review charts and see, okay, this reagent does this reagent does this, and just refresh it in your mind, because you know all of them. You forgot because you don't use them all the time. But if you look over them, they should come to you. And then when you do this packet, you'll start to realize what's doing what. You'll start to separate them more in your head. So that's what I would recommend. Okay, so we're already going on to electrophilic addition. So we've got many topics to cover. Okay, so predict the major product from the reaction shown. I'm kind of mad that I put this problem on here because I feel like it's kind of two of the same problems. But is this going to go Markovnikov or anti-Markovnikov? Markovnikov, right? We just did it HCl. So the only one really where the Cl adds to the same part is D. Yeah, it's just like the one we did earlier. I almost put two of the same problem on here. They're different, but yeah, this is also an orgo 1 reaction. Yeah, the anti ones are, they're usually, and this isn't like a law, but usually they're the exotic ones, right? Like if you're adding water, Markovnikov, you use H2O, H2O+. If you're adding an anti-Markovnikov, you got to use BH3, H2O2. Typically, that's not always the case, but if all else fails, go off that rule, right? Oh, this is basic. I'm going to go with Markovnikov. You can't remember. When you did orgo 1, I think you just had to memorize them. This was one of those things that was on that big chart. And you had to, there's not really like a rule that I could tell you, or not a rule that I remember anyways. Okay, so that being said, predict the major product of the following reaction shown. So now I have this BH3H6 H2O2 NaOH, right? So that adds water, anti-Markovnikov, right? Yes, I think this is hydroboration, if I remember. That sounds right. This one's adding 2 waters, or 2 OHs. That's wrong. This one's adding it Markovnikov. That's wrong. But you have 2 that are adding it anti-Markovnikov. And this is that whole syn versus anti addition. Does anybody remember if this is syn or anti? B is syn, right, and A is anti, but do we know which one? Anti is more stable. Typically reagents have something that they do. One does anti or one does syn. Hydroboration goes anti. So the answer is A. But yeah, anti is more stable. with which reagents can the ketones shown be prepared via a Diels-Alder reaction? So this is Orgo 2. You guys did this semester. One really quick way to answer this question is, if you remember, you need a cis-diene to do a Diels-Alder reaction. So nope, nope. Right? Those aren't dienes. You need 2 double bonds, and you need cis as well. Can't be trans. Yep, you need a cis-diene to do a Diels-Alder reaction. This is that, I think it's called Electrophilic Addition you did at the beginning of this semester. So I'm just going to go ahead and show you a really quick mechanism of what's going on in case you forgot. The what? I'm sorry. Yeah, this was in that chapter, but this was the electrocyclic section. So it's kind of just like pushing electrons around. I think it was like the easier part of the section, but it got less attention. So I always draw it with the diene facing it because it's easier to show. And you can just, I put my little dots attaching them. And then this one's going to make this bond over here. This one's going to be pushed out this way. And this one's going to make this bond over here. So that's going to give you this product. This one would have some weird bridge or something on it, right? Yeah. You have all of this in the way. We only use this guy to get our exact product. The answer is C. Any questions on this one? It was a short little section this semester. Okay. Okay, so nucleophilic addition. So what is the major product of the reaction shown? Now, I picked this problem because I feel like it's something that you guys have done, but there's so much going on that it might confuse you, right? You have 2 carbonyls, you have double N's right here, and you have an N over here, right? So it's kind of a lot. But the main thing that's actually going to react in this is just the double N's. They're going to make your hydrazone. So you guys remember that? It's like an imine, which is when you have an O and you change it to an N, right? It's like an imine, but with another nitrogen attached to it. This is a hydrazone. You'll most likely get a question about this because hydrazones are really important because you can use them for the Wolff-Kishner's reduction. If you guys remember, it's like zinc and HCl or something. I don't know. But it completely just removes all the nitrogens and gives you like a bare alkane. So it's a method to reducing a ketone down to nothing, is creating a hydrazone. So this isn't asking you all about that. It's pretty much just saying what are these 2 going to give you, and it's a hydrazone. They're asking questions about it just because it's important. So we're looking for that double bonded N that replaced an O. So right here we have the imine, but it lost the nitrogen, right? So that's not right, because we don't lose the nitrogen, we keep the nitrogen. This is the double nitrogen we're worried about. It's still going to have a bunch of other stuff attached to it, right? But it's not going to disappear. This right here has the hydrazone. You see the nitrogen replaced the oxygen, and then the other nitrogen is still attached, and everything else is still attached. So that's your answer. This one, again, you just have the imine and a loss of a ton of carbons. I don't know why. And that one, you have some kind of addition reaction, which would be a decent guess, but it's not correct. Any questions? Why can't it be D? Because that's the, I'm trying to look at what's happening there. That one is like adding the carbonyl. That one would be like if this like attacked, or no, that would be if this middle nitrogen attacked this carbonyl, which there's like nothing in your brain that's telling you that can't happen. But do you ever remember that happening? No, right? That's just something they're tricking you with, like, oh, this could maybe happen, but it never has happened before. So that's a tricky one. That's why I said it would be a decent guess. It's not like it's blatantly wrong. But the question this is asking about is the creation of a hydrazone, which you guys have seen before. So which reagent will accomplish the conversion shown? So this is a 1,4 addition, right? 1, 2, 3, 4. We're adding to the fourth right over here. What? Coupling? Yeah, it's carbon coupling. You're adding a carbon. So this is a coupling reaction. And it's a 1,4 addition. So what do we know does 1,4 additions on a ketone? We know Gilman's does, for sure. What else does? Any Michael donor, right? Any Michael donor will give you the 1,4 addition. That's what we just did that. The one we learned, though, all semester was Gilman's. That's the most basic one that we've been doing. That's one that's going to add this simple little CH3. And Gilman's is always the one with the Cu in it, the copper. Where would the Br add? I'm sorry, the MgBr, the Grignards add. It's going to add at the carbonyl, right? It's going to give you that alcohol carbonyl thing. I'm sorry, alcohol with the CH substituent on it. So that's the 1,2 addition. And then Gilman's is going to give you that 1,4 addition. You could also just use a Michael donor, which is kind of like the last thing we went over. It's the enolate chapter. Gilman's is technically a Michael donor, but we just know Gilman's as Gilman's because we've been using Gilman's for a while now this semester. How would, the Grignards? Grignards would, if I used this with CH3 MgBr, it would just leave my double bond alone. It's not interested in it. It's going to do the 1,2 addition. So my 1, my oxygen's going to get the H added to it, and my 2 is going to get the CH3. So this one would give me a tertiary alcohol. And there are plenty of questions on the ACS asking you how to make tertiary or secondary alcohols, and you need to work with your Grignards to get the kind of alcohol you want. So you should definitely know how to draw the product of a Grignards on a ketone. You should know how to use Grignards on an ester too. Know that the ester will leave. Know that it will go twice. Not in this case. Once you do it once, you're full of carbons, nothing's going to leave. You can't do it again. You can only really do it twice if you have a good leaving group. Or even like, I think aldehydes can go twice because they just have H. Ester will leave, yeah. So ester will go twice. Any other questions? Okay. All right, so this is a good one. What set of ketone for number 1 and aldehyde for number 2 will provide the same alcohol product 3 when submitted to the reaction conditions shown? So does everybody understand what the question is asking? Because that's like hurdle 1. Yeah, it's literally just asking, what do I start with to get here? But it specifies that number 1 has to be a ketone and number 2 has to be an aldehyde. So what ketone can I get using number 1's reagents to get to this product? And what aldehyde can I get using number 2's reagents to get to this product? So first of all, we know we have to use a ketone for number 1. What does LAH do to a ketone? It's going to reduce it to an alcohol, right? So that's a pretty easy one. We just need this ketone. And then when we use LAH, we're going to get our product. We're going to get the number 3, right? It's just going to reduce our ketone straight down to alcohol. So we can already eliminate C and A. Now, a trick to this problem without having to think about how anything is adding together is just counting your carbons. So if we're going to use an aldehyde with adding this MgBr to get to here, this part of our reagent has 1, 2, 3, 4, 5, 6 carbons. And our product has 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 carbons. So we need something with 4 carbons. So this one has 1, 2, 3, 4. This one has way too many.
So we can just pick B with that.
Oh, I lost my microphone. I hope this is recording good. Okay, so if you want, I can draw how the aldehyde would work and how you would get that product. But you can literally just do this problem by knowing that LAH is going to reduce your ketone down to an alcohol and counting carbons. You don't have to really visualize much. Definitely count your carbons. They won't always give you the answer. Sometimes, you are going to have to know some chemistry. But sometimes they can just give you the answer. So we like that. Any questions? Okay. Okay, so we're moving on to nucleophilic and electrophilic aromatic reactions. So you guys mostly did electrophilic. We did a little bit of nucleophilic towards the end. There was less emphasis on it, but the ACS has both questions on both. So you should definitely brush up on both. So which structure represents a major intermediate in the bromination of nitrobenzene? So this is our nitrobenzene. When you brominate nitrobenzene, that's just the Br2 FeBr3, right? Is that electrophilic or nucleophilic aromatic substitution? And you will get concept questions asking you either way, so you should know. Okay, is it going to go meta or para? Meta, right? If your deactivator, this is a trick, if you know your deactivator is making it go meta, it's electrophilic. Or vice versa. If you know your activator is making it go ortho or para, it's electrophilic. Those rules are the opposite for nucleophilic. You guys barely went over nucleophilic, but if you remember seeing something and you know in your head immediately, oh, this is going meta, it's most likely an electrophilic reaction. Yes? Yeah, so if your activator is giving you orthopara, it's electrophilic. And you should be confident in that, like, oh, I've seen this reaction before. If it's a nucleophilic reaction, it's the opposite. They're going to go the opposite way, so your activator is going to make it go. You need a deactivator to do a nucleophilic reaction, so it's a little different. But this is something you've seen before, and you instinctively go, oh, this is meta. If you get that instinct, it's electrophilic. So we know it's going meta, and we know it's electrophilic. Why is a deactivator deactivating it, right? Because it's pulling electrons out of the ring, because it's electrophilic. An activator is activating it because it's putting electrons into the ring, because it's electrophilic. Because the ring is what's doing your attacking, right? So if the ring is what's doing our attacking in this case, because it's electrophilic, and we know it's going to go meta, so I mean, first you can just cross these out, right? Because it's para. All we have to know is it a carbocation or is it a carboanion? And if this is an electrophilic reaction where your ring is doing the attacking, right? It's not adding electrons, it's going to have a cation, right? So it's going to be A. Any questions on this stuff? Okay. Yes? Why is it a plus? Because if it's an electrophilic reaction, and the benzene ring is acting as your electrophile, right? It's what's doing the attacking, right? And if you show this arrow, if you have this this double bond you can almost imagine it just shifting over and attaching to the Br, right? If this shift over and attached to the Br, this carbon would be naked, right? You just pulled that pi bond away from that carbon and added it to the bromine. So that carbon now is lacking electrons. It's going to be positive. It would be negative if you were attacking the benzene ring itself. Then you would be adding electrons to the benzene ring. But since the benzene ring is doing the attacking, it's what's going to have the positive. Nope, if it's an activator, it's still going to be a positive charge. It's just going to be the positive charge is more stabilized by the fact that you're donating electrons into the ring, if that makes sense. That's why it activates it, because it's activating that positive charge. It's stabilizing the positive charge by donating electrons. Okay. Any other questions on this one? Okay. So arrange in order of decreasing reactivity, fastest to slowest, towards HNO and H2SO4. So HNO2 and H2SO4. When you do that on a benzene ring, that's nitration, right? Do you guys remember adding an NO2 to benzene rings? That's an electrophilic reaction, right? When you add when you do nitration, it's electrophilic. So that being said, if something is activated, it should go faster because it's electrophilic. If something is deactivated, it should go slower. So toluene, right? The CH3, is that an activator or deactivator? It's an activator, right? It's a moderate activator. And then this double bond, this carboxylic acid, is that an activator or deactivator? It's a deactivator, right? It's a moderate deactivator. And then this Br, it's a weak deactivator. So note that the Br, while it is a moderate deactivator, it still gives you orthopara. Do you guys remember that as being an exception? Your halides, whether it's chlorine, bromine, fluorine, whatever it is, it's technically a weak deactivator. So when you're ranking things in speed of reactivity, you should note that. But as far as whether it's going to go ortho or para, it's going to go orthopara, even though it's technically a weak deactivator. Yes?
Could you determine if it's a deactivator by using electron donating group, like that trick, or is
I have them all memorized by now.
Oh.
But if something is donating electrons to the ring, it's an activator. So if that makes sense to you when you see that in your head, then that's a surefire way to go about it. That's the definition. If it makes sense that something is withdrawing electrons, like NO2, that's a deactivator. So if you see that, that's perfect. I just kind of memorized the chart, and I've been doing it so much now that I know them all. But and then this is just a regular benzene ring, right? So nothing's happening to that. So if we're going to rank them on speed from in decreasing order, so the first one's going to be the fastest, right? The fastest one is going to be the one that's activated. We're doing an electrophilic reaction. So that should have this 4 first, so it's either C or D. And then next, is it going to be the one that's deactivated that's faster, or the one that has nothing going on that's faster? The one that has nothing going on, right? It's like, imagine like running a marathon and someone put weights on your ankles. You're going to go slower, right? They're deactivated. So they're going to go slower than the guy he's just fine. So he's going to come after the moderate activator, so he's number 1. So the answer is C. And then between 2 and 3, this makes sense, right? Our weak deactivator is faster than our moderate deactivator. Our moderate deactivator has heavier weights, right? Slower in an electrophilic reaction, which this is. Nitration is electrophilic. We could write that if you want. Bromination, nitration, I guess halogenation or nitration are both electrophilic. Okay. Any questions on this one? All right, which would be the major product of this reaction? So what is this? Friedel-Crafts, nice. So Friedel-Crafts, you just add your carbons to the benzene ring, right? But remember, we have acylation and acylation for a reason. Acylation is the one that will rearrange if possible, whereas acylation will not rearrange. That's the whole purpose of it. In this case, we have acylation because we don't have that carbonyl. If you see a carbonyl, you know you're dealing with acylation. It won't rearrange. If you don't have a carbonyl, if you're missing all oxygens, it's acylation. This one is acylation. Acylation, it's the same thing with a C. That they didn't pick like. Oh, how does it look like? Yeah, so it would be the same thing. It would be like CH3, CH2, 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 Cl. It's also going to have AlCl3, but the carbon that you're adding should have a double bonded oxygen to it. I guess this would have less hydrogens, right? Oh, I'm sorry. So this would be acylation. And then remember, if you wanted to get that regular carbon on there, like the regular carbon chain, you don't want that carbonyl on there, you have to reduce it. So usually you see acylation with 2 reagents because typically you just want the carbons. And I believe that reagent is zinc, Hg, is it like HCl? I don't know, I'm gonna put a star. So I think it is. And that's just gonna get rid of the carbonyl. So that way you added your carbon chain and there was no rearrangement happening, that's acylation. All this does is get rid of the carbonyl. All this does is add this carbon chain without any rearrangement. And we're going to see in this acylation, after we lose the chlorine, right, the chlorine leaves, we're going to get a positive charge right here. But that positive charge is going to rearrange, right? It's primary. The carbocation is going to go ahead and go secondary because it can. There's no carbonyl stopping it from doing so. So it's just going to go ahead and shift right over here. So now you have this intermediate. That's a CH. I always mess up my H's. So that one's so your product is actually going to have it added on the more stable carbocation rearrangement versus your additional rearrangement because you used acylation. That's the purpose of acylation, so you don't get that rearrangement. But we used acylation. We had no carbonyl. So we are going to get the rearrangement product as our major product. You will get a little bit of this one, of course, but it's asking for the major, right? So it's going to be B because that's the one where it added to your benzene ring on that rearranged carbocation, that secondary, more stable. Any questions on this one? Okay. Okay, so this is a good one. So this is saying which aryl, is that what that is? Aryl chloride reacts fastest with NaOH? What is NaOH? It's a base. Is that what you said? Yeah, definitely. What else is it? Is it an electrophile or a nucleophile? It's a nucleophile, right? You said it was a base. That's because you typically see it like this, right? The Na leaves, that's negative, right? That's a nucleophile. It's going to want positive charges. It's not an electrophile. So this is an indicator that you're going to have a nucleophilic reaction, right? This is actually going to attack your benzene ring versus your benzene ring attacking it. It has no sigma positive charge like a Br2 does. It's all negative. It's what's going to be doing the attacking, right? Electrons do the attacking. So this is a nucleophilic reaction, which you guys did a little bit less of. You did a little bit less of nucleophilic aromatic substitution. So think about it. If I'm adding electrons to my benzene ring, do I want it to be activated? Do I want it to have more electrons in there? No, right? It's going to be more stable to have stuff deactivating it, right? So we see we have a ton of NO2s on here, right? These are deactivating my ring. So these are actually going to make my nucleophilic reaction faster because they're going to be deactivating it. They're going to be pulling electrons away when I'm adding electrons to it. So we can cross this one out automatically because it has no NO2, and we can cross this one out automatically because it only has one. Now this is the, oh, I dropped my microphone again. Okay. Now this is the part of the reaction that, or the question that's a little bit more tricky, is it better for them to be in meta position or ortho-para position? I'm a nerd, so I just memorized it when I took the class, but I can show you the resonance structures, so it makes more sense. But you guys, if you had Fraser at least, you had to draw the key intermediates, right? You had to draw all of those positive charges and where they're more stable. Same principle for your negative charge. You're going to want it on your substituents. You're going to want it next to something that's withdrawing the electrons. Meta gives you it away from your substituents, whereas ortho-para gives you it right on it. So I can show you what I mean by that. You also need a good leaving group for nucleophilic substitution. If you don't have one, it's via the benzene reaction. I don't know if you guys remember that. That's that weird triple bond thing. But anyway, we have one. We have a Cl, right? And we add our OH where the Cl is, because the Cl is going to leave. And that's going to say we have it like this and like this. That gives us our negative charge on our NO2, right? Which is good, because now it's in the place where it has electrons withdrawing from it. So that's more stable than if it was just on a carbon. Do you see how if these were meta, so if this was over here, the negative charge wouldn't be on the NO2. It'd be further away from my electron withdrawing group if my nitrogen was in the meta position. So it's not quite as stable. And then even in the resonance structure, my electron withdrawing group has a negative charge next to it if it's orthopara. Again, if it was meta, and if this was over here, it's not going to have that negative charge on it. That's never going to happen. That's the purpose of orthopara, is so that whatever charge you have, whether it's positive because it was electrophilic or negative because it was nucleophilic, it's next to your substituent. In this case, it's good because it's nucleophilic. We want it next to the electron withdrawing group. So that's why the orthopara is the correct answer. The same principle goes for electrophilic reactions. You get orthopara because you want your positive charge next to your donating group. You get the same resonance structure. Yes?
We already know that meta is for the activator, so we wouldn't. That's why we wouldn't choose B, right?
Meta is for activator? In this case, for nucleophilic additions, you actually need a deactivator. If you don't have a deactivator and you don't have a good leaving group, it's that weird benzene thing I was talking about. But I really didn't see much of it on the ACS, so I wouldn't worry too much about that.
Actually, the activator it should be orthopara, right?
Yeah, I mean, if you added the Cl first, they would have added orthopara, but you could have easily have added the NO2s first, and then you would have got the meta position. So you could create either of these benzenes. It's just a matter of which one is going to make it go faster. And so that's the one where your intermediates have the more stable resonance structures. Any other questions? Okay. So, which sequence of reactions is expected to give the best yield for 3-nitrobenzoic acid? So these are meta, right? We can note that first of all. So we're going to have a deactivator on when we add something. So let's look at the first one. I have a nitrogen on my benzene ring, and then I'm doing alkylation to add a CH3. That's going to go meta, right? Is it? It's not going to go at all, right? You can't do alkylation or acylation. You can do no Friedel-Crafts on a deactivated ring. They have to either be a naked ring or an activated ring. Actually, you can do it with a weak deactivator. You can do it if it has a Br or a Cl. But anything moderate or above, you cannot do Friedel-Crafts. So the first one isn't going to work because your Friedel-Crafts is not going to go on your moderately deactivated ring. It's not going to work on your nitrogen or your nitrobenzene. So we can look at the next one. What is sodium chromate going to do to this CH3 toluene? It's going to make it a carboxylic acid, right? So our first one's going to be like this. Now I have this carboxylic acid. Is the carboxylic acid an activator or deactivator? A deactivator, right. So when we do our brominate or our nitration, which is what this is, which is electrophilic, on a deactivated ring, it's going to go meta. Which is going to give you your answer. C is wrong because your ring is activated to begin with, right? You didn't do your sodium chromate first. You didn't make it a carboxylic acid first. So when you do your nitration, it's going to go ortho-para. It's not going to go meta. So C is wrong. And then D is really tricky because it's like the right order, and this has an N in it, so maybe it's working the same way, but this isn't the reagent that we use to do nitration, so that was a little tricky. You had to actually know which reagent does nitration to pick between B or D.
Is it like KMNO4?
Yeah, it's working just like KMNO4.
But isn't it that one that cuts? No.
It's doing the same thing. Yep.
Position. But here it's doing another job.
It's doing the same thing. It's taking the CH3 and it's making it a carboxylic acid right at the.
Did you say deactivated rings add meta?
Deactivated rings add meta, yes. So we made it a carboxylic acid first with our sodium chromate. That's a deactivator. Then we're going to add our nitrate. That's going to go meta. Then C, we had a toluene on it at first. That's an activator. So if we nitrated it right away, it would have gone orthopara, which is not what our product is. Our product is meta. So it had to be B. D is technically going to give you meta as well, except for the reagent is wrong, so it's not going to. So you had to know the reagent. Any other questions? Okay. Okay, yay, spectroscopy. Everyone's favorite, right? I like spectroscopy, but I think I'm the only one. Yeah. Okay. Which is the most reasonable structure for the compound with this IR spectrum? So, something to note. I'll start writing some values down for you guys. A triple bond, I'm just going to draw an arrow because if I draw an equal sign, then it's going to look like a double bond, is around 2,250. And I'm sorry, but you kind of have to know these numbers, at least for this exam. They have, if you look on your ACS study guide, I wish I would have brought it with me. The first page, literally the first page in spectroscopy. Actually, I think I did bring it with me. I could show you really quick. The first page in spectroscopy has a nice little list of numbers right here for you guys that you would need on the ACS. So instead of Googling like IR spectroscopy numbers and looking at a chart of 500 of them, look at your spectroscopy page on your ACS or take a picture of this. Hold on, let me get the bottom one in because there's also the H Nmr numbers as well. Very helpful. If only 45 minutes before the exam you cram these numbers in really quick, memorize them for the exam and forget them, do it because it's going to help you on a lot of problems that are actually easy. You just have to know numbers for. So if you need to do well in this exam, I definitely recommend that. I think those are all the ones they have. Yeah. Oh, they have carbon NMR, but I don't think you really need those numbers. But if you want them, I'll show them to you. Does anybody want these? No? Okay. Okay, cool. So that being said, we have our little chart, right? We have some numbers. I said 2,250 around there is your triple bond. And if you look on our chart, we actually have a pretty nice peak around that 2,200 section, right? So that's indicating that our molecule has some kind of a triple bond in it, right? So we can initially just cross out D because it's only a double bond. It has no triple bond in it. That's not going to give us the signal that we have. Something else that you should notice, if your IR spectra isn't giving you much, look at your products and see what they should be giving you, right? B has an alcohol. You guys remember alcohol gives you that really broad thing over here in the 3,000 mark? We don't have that, so it can't be, there's no alcohol present because we're missing the sign for an alcohol. So now we're between these two triple bonds. Now, you guys are going to hate this, but you can actually tell the difference based on the whether it's a terminal or an internal, I think that's what they call it, triple bond. So the terminal triple bond has this sp hybridized H. If you look on your chart, sp hybridized H's give you a signal around 3,300. So all of these signals that are right here, at like right below your 3,000 mark, are always going to be just your regular CH bonds. If you have a CH bond on a double bond, you should see a little peak a little bit higher. And if you have a CH bond on a triple bond, you should see a little peak even a little bit higher than that, right? And your chart says that. It says sp, sp2, sp3, right? If we had this product, we would have an sp3 CH, or I'm sorry, we'd have an sp CH bond, right? So we should have something that has an IR absorption of around 3,300. And we don't. They all stop right here at the 3,000 mark. So the answer has to be A. It has to be an internal triple bond. Now, of course, your carbonyl is giving off a signal right here at 1720, which is like the one that we all memorized. But unfortunately, in this problem, it doesn't help you at all because all of the options have carbonyl. Why did I eliminate D? Because D has a double bond, not a triple bond. And I think the double bond number is like 1650 or something. Let me double check. 1600. No, that's an aromatic double bond. It doesn't show, so apparently you don't have to know it. But it's not 1720. And it's definitely not 2250, which is the triple bond mark. And we have a clear peak at the 2250, so we know we have to have a triple bond. And D doesn't have any triple bond. It just has a double bond, so it can't be D.
What's the difference between the CH, like when it comes at the end and when it's not?
So when there's a CH at the end, when it's terminal, that means you have an sp hybridized H, right? Do we see that? The H is going to be at a 180 angle. It's going to be straight. That's called sp hybridized. Because of the triple bond right next to it, exactly. If there was no triple bond next to it, it would just be a regular old hydrogen. Because it's terminal, it has that H or that sp configuration. And if it has that configuration, it should show a peak even higher than the 3000s. These peaks right here are your regular CH bonds. If you have any that's on a double bond or a triple bond, they should be a little bit higher than that. They should be around 3,300 for sp and like 3,100 for sp2. Does that make sense? So because we didn't see that, we knew it had to be internal. We knew that it couldn't be terminal because we're missing that sp-CH bond peak. Any questions? Feel free to ask questions because spectroscopy is a big part of the exam. And I feel like you guys kind of forgot it because you learned it in Orga 1. Yeah, so definitely ask any questions if you have some. Okay. This is a good one. This is like the ugliest little H Nmr graphs I've ever seen, right? They have like barely anything on them. But the purpose of this question is to determine whether or not you understand integration values. They have the little numbers on them, really tiny, but I just wrote them on there so you guys could see them. When you have a number on top of your multiplet or triplet or whatever your signal may be, and it has a number with the letter H next to it, that's your integration value. So first hurdle is recognizing that that's the integration value. These little 3H, 3H, 2H's are your integration values. Do you guys remember what integration values do, what they are? Integration values are the amount of hydrogens giving rise to the signal. So how does that differ from multiplicity? How does that differ from a triplet or a singlet or a doublet? Exactly. Multiplicity is dealing with the neighboring hydrogens. So multiplicity tells you how many hydrogens, multiplicity, you have on the carbons next door, right? Integration values tell you how many hydrogens themselves are giving rise to the signal. So, it's not really useful for this question, but it definitely will be. What does chemical shift tell you? Like, so chemical shift means, where are these signals? Are they further to the left or downfield? Are they at the bigger numbers? Or are they upfield, further to the right? Do they have lower numbers, right? What pushes your signals towards the left? What makes them at higher numbers, at higher ppms, right? H Nmr is on a ppm scale. Exactly. Electronegative heteroatoms next door. So oxygen, nitrogen, you know, all of those guys. So electronegative neighboring atoms. They push your signals to the left or at a higher ppm. Same thing. These are the same, just whatever makes more sense to you. Going more to the left or at a higher number, right? The bottom is numbered. Okay. That's pretty much all you're looking at for H Nmr. Remember, this is H Nmr, so this is not, clearly this isn't useful for IR spec or mass spec, right? Those are different. But for your H Nmr questions, which there's a lot of them, these are like the 3 things that you could know to help get you through all of the problems. Any questions on these? The difference or anything? Okay. So to answer this question, we're given integration values for each signal. We're given multiplicity, and we're also given ppm, but it's only on a scale of 1 to 3. Usually it charts all the way up to 10, so there must not be that much of electronactivity going on in here. So if we look at our compound, we have a CH3, right? So all 3 of these hydrogens are going to give rise to a signal, right? So they should have an integration value of 3. Are they going to be a singlet, a multiplet, a doublet? What kind of multiplicity are they going to have? Pretend that this S is an oxygen. Do your signals go through oxygens? No, right? So it's going to be a singlet. There's no neighboring carbons. There's no neighboring carbons that have any hydrogens next to it to affect its multiplicity. So that's going to be a singlet. That's going to be a singlet with an integration value of 3, because it's 3 hydrogens with no other hydrogens next door. Does that make sense? Okay. So then moving on, we have these 2 hydrogens right here. Can I look to the right? No, right? It's not going to go through the S or the O or whatever that atom is. So all that's affecting it is the ones to the left. And that's a CH3. So our rule for multiplicity is n plus 1, right? So I have 3 hydrogens next door. That's going to be a quartet. Does that make sense? So that's a quartet with an integration value of 2, because I have 2 hydrogens that have 3 hydrogens next door. Right? Makes sense, not hard. Okay. Then we look at this last one. That's 3 hydrogens, right? All 3 of these hydrogens are in the same place. They're going to give rise to the same signal. So that's an integration value of 3. And how many hydrogens they have next door? 2, right? So 2 plus 1, right? So these 3 hydrogens should give me a triplet. So I should have a triplet with an integration value of 3. Does that make sense? So that's what we're looking for. So if we look at letter A, we have 3 hydrogens that are a quartet. Do we have that? No, we don't have that. We have 3 hydrogens that are a triplet, and we have 3 hydrogens that are a singlet, but we have no 3 hydrogens that are a quartet, right? This is 1, 2, 3, 4 signals. So we can instantly cross that one out. Here, we have a triplet that's 3 hydrogens. Do we have that? Yeah, right? That's this guy right here. He's a triplet, and he has 3 hydrogens next door. I'm sorry, 2 hydrogens next door. So triplet of 3 hydrogens. Then over here we have a singlet of 3 hydrogens. Do we have that? Yeah, that's this guy right here. It's 3 hydrogens, but no hydrogens next door. It's a singlet. And then this last one, we have a quartet of 2 hydrogens. Do we have that? Yeah, that's this one in the middle. That's 2 hydrogens, but it's a quartet because it has 3 hydrogens next door. So the answer is B. And we can go through just to make sure. This is 2 hydrogens of a triplet. We don't have that. our only 2 hydrogens are a quartet. So that can't be right. And again, we have 2 hydrogens of a quartet. That's right. Oh, maybe I drew this one wrong. Oh, well, actually, if I drew this one right, the way you have to tell is that your quartet is next to the electronegative atom, right? It's next to the S. So that's going to push it further to the left. In this answer, you have your quartet further to the right, right? Does that make sense, that last step, why it has to be B and not D? I think when I was doing this earlier, I didn't notice that, but yeah, this technically has the right amount of multiplicity and integration values, but because your triplet is the one that's furthest to the left, it can't be right because your quartet should be further to the left because that's what's closer to your most electronegative atom, and electronegativity is what pushes it to the left, pushes it downfield, higher ppm. Any questions on that last step or this question at all?
This is a singlet?
Yep, that's a singlet.
With a value of 3?
Yep.
Integration?
Yep.
Why?
So
because
that's
it has just 3.
because it's 3 hydrogens that are giving rise to the signal, right?
But we're looking for one thing.
Yeah, exactly. So it had an integration value that said 3H. Is more visible on the exam somehow. It came out blurry. But it's 3H, right? So it has an integration value of 3, but it's a singlet. So that's this guy.
Okay.
That makes sense?
Yep.
Okay. Any other questions on this guy? This question? I don't know why I'm turning them all into persons. Okay. All right. So, which structure is consistent with this H Nmr spectrum? So this is a good one, right? This is a more complex of H Nmr questions. Notice they don't give you any integration values. You don't have to worry about them. You don't need them to tell the difference. If they don't give them to you, they're not there. I think they're helpful, so I find it annoying when they don't give them to you, but most of the times they actually don't give them to you. If they do give them to you, then you need them to answer the question. Okay. Oh. So the first thing I noticed, can anybody tell me what the first thing they noticed? Did they notice anything like staring or glaring out on this NMR spec? No. What about this one? It's so far out here to the left, right? What could it possibly be next to that's putting it all the way out to 10 ppm? Yeah, oxygen. OH, if it's just a regular oxygen, I think is like 3 to 5. Let me just double check. I have a little chart right here. Yeah, it's like 3 to 5. 3 to 6 it says. So it actually has a pretty wide range. So actually OH is not very telling. But is it more electronegative to have a double bond on an O? Yeah, right? Now you have even more electrons in that same area, all condensed in that same area. So actually if you have an aldehyde or a carboxylic acid, these H's are really electronegative. They're going to give you a range from like 9 to like 12 even. Carboxylic acid being, of course, a little bit more electronegative than aldehyde, right? Because you have that extra O there. So I wrote it that way on purpose. There is kind of a gray area, but if you had to distinguish between the two, the carboxylic acid is going to have a higher ppm. It's more like carboxylic acid 11 to 12, aldehyde 9 to 10, but again, there's like a bit of a gray area. So that being said, we have this little bond or this little signal all the way out here at the 10 mark. Means we probably have some kind of an aldehyde, right? Or carboxylic acid. This one has an aldehyde, so that counts. This one is an ester, right? H Nmr measures H's. So really, it's not that effective. It does not push it all the way down that far like an aldehyde or a carboxylic acid would. This this one also has a carbon or an aldehyde, and then this one's just a regular ketone, right? So that doesn't give us that signal. So before looking at multiplicity and all of that gross stuff, right, before going through everything on all of them, we initially just crossed out 2 answers. That's huge. You will definitely see questions like that where, knowing that it's a carboxylic acid or an aldehyde crosses out 2 answers, super helpful. Sometimes it gives you the whole answer. Any questions on that first step? Really important. Okay, cool. Now, how do I distinguish between these two, right? What? There's a couple ways you could do it. I'm going to show you what I think is the easiest way. And that's just based off of number of signals. So I know I didn't really show you that, but if you think about it, logically, how many signals that you have is based on how many different kinds of hydrogens you have. That make sense? Right. So if we were to count the number of signals, and you will definitely 100%, I'm not even kidding, at least one problem that's like, how many signals does this compound give off in an H Nmr spec? How many signals does this compound give off in a C Nmr spec? So you definitely need to know how to circle symmetrical and similar signals. Okay, so we're doing H Nmr, so we're looking at hydrogens, not carbons. So how many signals does this one give off? I have an H right here, that's 1. Do we agree that both of these H's are going to give off the same signal, right? That's 2. These are also going to give off the same, right? That's 3. Do I have an H here? No, right? Do I have H here? Yeah, I have 1. Is it also going to give me the same signal as that one? Right, so that's another one. And then what about right here, right? These are their own signal. They're a little bit further from everything else. And then also, don't forget, I have a little hydrogen on the tail right here. That's also its own signal, because it's a little bit further from everything else than the other 2 hydrogens that preceded it. So how many signals is that? That's 1, 2, 3, 4, 5, 6. How many do I have? This is not a signal. Know that. Not a signal. Tells you nothing. It's like a calibration signal. And they put it on there just to test if you know. So I only have 1, 2, 3, 4, 5 signals. So either I counted wrong or that's not the answer. So we'll move on to the next one, double check. I have 1 signal, 2 signals, 3 signals, 4, and 5. So the answer is C. Yes? Why did I circle the H's on the nitrogen? Yeah.
Why do you circle the H's?
Just to show that that was what's giving rise to the signal. Those H's, whether it be on the aldehyde or the carboxylic acid, is what's giving you that 9 to 12 signal. It's that H or that OH. Something to consider, this is definitely a super side point, but something that I get wrong all the time for no reason. When you're looking at an aldehyde, this is the carbon it's attached to. So it doesn't necessarily have to be a singlet, right? You're going to look at the next carbon from the carbonyl. A lot of times I'm like, oh, it's on a carbonyl, it's a singlet. Not true, right? Look at the next carbon over when you're looking at an aldehyde. Carboxylic acid is always a singlet, right? Because you don't go through the oxygen. Aldehyde, you're actually on this carbon, so it doesn't always have to be a singlet. Does that make sense? I get that wrong all the time, or at least I did when I took that class. I would just assume aldehyde's a singlet, and that's not true. Okay, any other questions on this? Another way you could have answered it, a little bit more complex, but maybe this will make more sense. You have 2 doublets, right? Each of these hydrogens on these benzene rings, right? They each have 1 neighboring hydrogen. Do you see that? This one has 1 hydrogen over here. This one has 1 hydrogen over there. These are the 2 doublets, right? These are the 2 separate doublets. In this case, you have this other hydrogen, which is going to mess everything up, right? Now this hydrogen is no longer a doublet. It has a hydrogen over here and a hydrogen over here. So that would make this signal wrong. If you only have 2 doublets, it has to be parallel. You have to have 2 signals that only have 1 hydrogen next door. Does that make sense? If you don't see that, that's okay. Counting the signals worked for this particular question. But like, don't let all of that stuff confuse you. Like, those were some big compounds, and you would be like, how am I supposed to decipher this? When really all you needed to do was notice it's an aldehyde by that one little baby signal and count the amount of signals, and one of them had too many. That was it. So a lot of times there's just little tricks to answer them, and you don't actually have to be able to like replicate an H Nmr spec of your compound. Like, I don't even know what the nitrogen would do. I don't know. We're not worried about it, right? Okay. All right. So this is another one that seems super hard, but it's actually really easy. I went over it in my SARC session, so I apologize, but I felt like it was a good one to show because it seems like, oh my gosh, I'm just going to blindly guess. But actually, you don't have to know anything about the numbers. All you have to know, this is C NMR, right? So we're looking at the carbons now, not the hydrogens. But the same principles apply. Not multiplicity, but the same electronegativity chemical shifts principles apply. So a carbon that has more electronegative heteroatoms around it is going to be shift to the left, thus have a higher, I think it's still on ppm, it might be different, but a higher number if it has more electronegative atoms around it. So we can just actually use that principle to answer this problem without knowing what the numbers should be at all. So an easy first step is like noticing out of all 4 of these carbons, which one should have the highest number? 2, right? 2 is surrounded by this double bonded O, another O, and a nitrogen. It's going to be so high up there. It has all these kinds of electronegativity affecting it. So that should have the highest number. So what you can do right away is look which one of 2's don't have the highest number. A and B, right? Only C and D have 2 with the highest number, carbon 2. Does that make sense? So we just eliminated 2, super easy. We didn't have to know anything about our carbon table. We just used like the basic principle. So now how do I distinguish between C and D? Well, we can use the same thing, right? Out of 1 and 4, which one should have a higher number? 1, right? 1 is right next to an oxygen. 4 is all the way out here. It has way less electronegativity affecting it. Number 1 should have a higher number. So between C and D, which one has 1 with the higher number? D, right? In D you have a 51 versus a 15. In C you have a 15 versus a 51. So that's why D is the answer. Does that make sense how I answered like what seemed to be a hard problem, made it super easy? All I did was look at electronegativity. Try and think about that. A lot of these questions are like hidden concept questions, and they're not too bad. Any questions on this? Perfect. All right, we are on the last section. We are on synthesis. We might even get to do some bonus problems. Yeah. I'm sorry I didn't give you more on your review. I thought this would take longer. Okay. So which is a major product of this reaction sequence? This is pretty much all Lorga-1, but aside from the last reagent, I feel like you guys can use your logic to get through it. So I have a C6. I'm going to write it actually on a separate paper. So I have a C6, H5, C, triple bond to CH. And my first step is Na and H2. Is that a base or an acid? Or neither? What do you think? Base, right? If I lose my Na, now I have this like negative nitrogen, right? That's definitely a base. That's a strong base, actually. Do we see that? Na always leaves no matter what it's on. Just a salt pops off immediately. So, you know, in essence, what you're looking at is NH2 negative. So that's a base. What do you think that's going to do to the thing on the left? Deprotonate it, right? So this is an Orgo-2 reagent. I personally didn't memorize it. I don't remember at all, but at one point you did. But I figured, oh, this is probably going to pull an H off, right? This is a really strong base. It's probably going to pull my H off. That's all it does. So we just have this. right? Now, let's do it like this. I have a CH3, CH2, CH2Br. What is that going to do to my negative triple bond? What do we think? It's going to like attack, right? It's just going to attach right on. We have a good leaving group. This all makes sense. You know, we probably don't remember what an alkyl halide does to a negative triple bond, but would we guess that that's probably what would happen? Makes sense, right? So carbon coupling is happening. So we're this far. Now this part is the part where you kind of have to memorize the reagent because it's like a nickname. You can't really use any hints. H2 signals that you're doing a reduction, so at least you kind of have that clue, right? You have an H2 platinum usually gets rid of double bonds, right? Do you guys remember what Lindlar's catalyst does? It does reduce to an alkene, cis, right? That was the big deal in Orgo 1, was like, remember, Lindlar's catalyst is the only way to get that cis alkene double bond, right? So definitely memorize this reagent. If only for this exam, it'll probably come up. It was like a big deal. It's like the only way to do it. And there's no way you can know it. You just have to know it. Like, you can't figure it out. It's one of those things. So this has a cis double bond. We just have this double bond. Cis meaning that we have the bigger priority groups going in the same direction, which of course is going to be the carbons, not the hydrogens. So that's what we're looking for, right? Something with this cis alkene double bonded thing. So we can look at our products. This is the same thing but trans, right? We have one going up and one going down. Do you see that? So that can't be it, right? Because Lindlar's always gives us cis. Is this the same thing but cis? Right? I may have written mine with the H's on top. Makes no difference. The only thing that matters is that they're both going the same way. Think if you had this in like Microsoft Word and there was like a little arrow on it, you could just rotate it 180 degrees and they'd be the same, right? So the answer is A. Just to clarify, this one is tricky because H2 platinum does reduce it all the way down to an alkane. So if you didn't remember, you might have been tempted to pick that. But that's not the correct answer. That would be like H2 platinum, or I think it's like H2PD. I don't know what PD is. I think it's platinum or plutonium or something. H2PD is what reduces it down straight to the alkane. We don't have that. We have Lindlar's catalyst, which does the alkene. And then this has some weird kind of rearrangement going on. There's no rearrangement. That doesn't happen in this type of reaction. Yeah, if it was H2PD, you would get just a plain alkane. Yep, that's going to reduce your triple bond all the way down to no double bonds or triple bonds or anything. Whereas H2, Lindlar's catalyst, gives you the cis alkene. I don't remember the reagent that gives you the trans alkene. I think it's some kind of like sodium something, like a metal. Yeah, oh, is it ZnHg? Is it the one with the silver? AG, I don't remember. I'm gonna be honest, I don't remember, but there is a reagent that gives you the trans alkene as well. I would know that one too. I know the one that adds a carbonyl to a triple bond is H2SO4, HgSO4 in heat adds a carbonyl to a triple bond. I know Lindlar's and I know H2 platinum, but I forget the trans double bond. So I'd look into that for sure. It's a good one to know. Okay. This one, it's not hard, but it's like one of those that's like time consuming, right? I don't know if the way I did this was the best way to go about this, but I immediately just started numbering my carbons to try and like figure this out. I'm not really good at like imagining things. I always get it wrong, so I just put numbers on stuff, so it has to be right. So I just kind of ignored the methyl groups for numbering purposes, and I just numbered my my base carbons, and then I would take note of which base carbons had like any kind of methyl or anything on them. So I have 13 base carbons. It's a good start. First of all, we're doing what we just did, right? We have a triple bond and we're using Na, NH2. So we're removing the H, right, on our triple bond, and then we're using a Br with some kind of alkane. So clearly the ACS likes this reaction. So, you know, be comfortable with it. And then remember how I just said that H2PD is going to reduce it down to an alkane? That's what they're using, right? So they literally pull an H off, stick them together, and then get rid of the double bond, the triple bond, to give you this product. So it's saying which one of these does that. So pretty much we're just counting carbons here, seeing which ones, when I glue them together, are going to give me that product that I want. So the way I did it is I just started numbering these guys and seeing if it like matched up at all. So this one has like a 1. First of all, this one has 2 bromines, which is just a red flag to me. Why are there 2 bromines? That doesn't seem right. There would probably still be a bromine on it, but even without that, it's still wrong, right? Because you have 1, 2, 3, 4, 5. 5 should have a methyl, right? It doesn't have a methyl here. That's just going to become a regular carbon-carbon bond when I use my H2 platinum. So this one's wrong for all kinds of reasons. Not right. We go to B. We have 1, 2, 3, 4, 5. Hold on. I numbered it wrong. Haha. We have 1, 2, 3, 4, 5, 6, 7, right? 7 has a methyl, right? So that's a contender. Like the starting product looks like it's going to be right. I can see it has a methyl where it should be. And then I kept going. I said 1, 2, 3, 4, 5, 6. It doesn't look right. It looks like it's missing a methyl. I kept it just in case maybe when I added them, like I could flip it around or something, but it didn't seem as promising, so I was like leaning towards B. And then this one's weird because it has 2 triple bonds. And I thought, well, okay, that could work. It has 2, molar equivalences of each one, and I'm deprotonating both sides, and then I'm plopping those 2 little like fishtail things on the end. So like maybe that would work, but made me make sure that everything is right. And when I counted them, I realized this one has 1, 2, 3, 4, 5, 6, 7, 8, 9, and then it would be plus 2 base carbons, so 11, and I need 13. Do you guys see that? How it doesn't have enough carbons, even if I was to add it. If I was to add another like little fishtail right here, it wouldn't be enough. It would be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. And I need 13. So that one's definitely wrong. So now it's just between B and C. And now if I add this Br right here, I would have 1 methyl sticking out because I'm missing the one on 5, and I need 2. I need one on 5 and 9. Do you guys see that? Right? So that one's missing a methyl. If I add this one on here, right? Say this is at 7, it's going to add on the bromine side, right? So if we're numbering it according to this one, this would be 8, 9, 10, 11, 12, 13. I have this methyl on 9 and this methyl on 5, right? So that one's going to work. They're going to glue together perfectly. My methyls are going to be in the right place. C is, the only problem with C is that it's missing 1 methyl. It's missing your methyl on the carbon 5 or carbon 9. I mean, it's symmetrical. It depends on how you number it. But in this case, it's missing the methyl on my carbon 5. So B is the correct answer. Any questions on this one? This is a tricky one just because you have to like count carbons and stuff, but we're good? Okay. And if you could see it, I mean, you can see it, go for it. But that's probably why I took the entire time to finish my ACS exam. Okay. I love this one. So I have this first reagent is already like being tricky. Like, what is that, right? I have a CH2, CO2, CH3, and I have 2 of those. Do we see that? Now, this is a CH2, right? If something is a CH2, it means it must already have 2 things attached to it. Does that make sense? So one of those things in the parentheses is going to be on one side of the CH2, and the other is going to be on the other side of the CH2. Why they chose to wrote it like that, I don't know. Testing you guys, I guess. But so we would have our CH2 in the middle, and then that's going to be bonded to the C. It's O2, so that's OOCH3, right? And then we have another one, CO2, CH3. What does this look like? Malonic ester. Yes, you guys just took a test on this, right? So this is a problem that you should get right. You just took an exam on it, but the first reagent could have like messed you up. But it's not bad. Just think about it a little bit. It makes sense. So we should be good, right? We should be able to do this. We have an NaOCH3, or Naomi, you know, whatever you're used to. I always call it Naomi. What does that do? It's going to deprotonate the carbon in the middle, right? Alpha carbon. Okay, and now, this is funny because if you had Fraser, this was on your exam. I have a BrCH2, CH2 with another Br, right? It's flanked by 2 Brs, okay? So I'm going to draw it like this just so that ease of mechanism. So this is going to attack this carbon, right? And then this Br is going to leave. Does that make sense to you guys? That's how it usually adds, right? That's alpha alkyl bromination. I'm sorry. Alkyl halogenation or something like that. So then we have OCH3, CO, CH. This has a CH2, CH2, Br. And then this still has all of this going on. Hello. So what do you guys think is going to happen next? We have that Br hanging off of our alkyl that just added. Do you think that's going to be useful? Do you think it's going to do anything, or is it just going to like hang out? Something to note is that we actually have half a molar equivalent of it, which is a really tricky way to say you actually have 2 times as much base. Does that make sense? So for every one of those, you have twice as much base. So you're actually going to get deprotonated again and be able to attack this again. And then it makes a little ring. Does that make sense to you guys? Okay, so it's just going to go all over again. We'll have our like Naomi pull off the hydrogen. And then we're going to attack our carbon, and our bromine's going to leave. And then these are a little sloppy. Okay, so now we're going to have this. Does that make sense how I got there? I know this is a little tricky one. But something to remember is when you do malonic ester synthesis, you can't go twice. You can't pull both of those hydrogens off. And typically, we were adding things separately. But if you have two bromines or two halides on the same alkyl substituent that you're adding, of course, you can't go twice within the same compound. You're just going to make a ring, you know, intramolecular, right? And then the last one is the H 3O plus and heat stuff. And what is that going to do? It's going to do the decarboxylation, right? So the H3O plus is going to make them both OHs. And then the heat is going to cut off one half. It's going to cut off the CO2. So that's going to give us our carboxylic acid product that we expect when we do malonic ester synthesis. Does that make sense? Oh, I dropped my microphone on the floor again. I'm sorry. Okay. Any questions? I know that was a bit of a rough one. I honestly have no idea. I would ask, there's a little desk, and I hate to send you all the way back downstairs, but there's a little desk right by the, what's it called? The coffee place.
Oh,
Cafe Bustelo.
Oh, okay.
There's a little thing right by Cafe Bustelo, and yeah, they're the study union like coordinators, and they'll tell you exactly where to go. It's fine. Okay. So, it's got to be this one, right? That's the one with the triangle in it, carboxylic acid. When I tried to do this problem, I tried to be slick and be like, oh, it has to be carboxylic acid. I'll cross all the ones out that aren't carboxylic acids. But they all have carboxylic acids. So you really had to know what was going on to get this question right. That was a rough one. But I thought it was fun, so I wanted to do it. Okay, we're on our last question. Yay. And we still have a good amount of time left, so we'll definitely get to do some more extra questions. I'm just going to do them. I have like bits and pieces of the ACS study guide, so we'll just do whatever topics you guys want help with the most that I have. So for this last question, we have, predict the major product in this reaction. Could be a little zoom in. So first we have the toluene, right? The benzene ring with the CH3 on it. And we're using KMNO4, NaOH, and heat. And what is that going to do? Exactly. It's going to give us our carboxylic acid in the benzylic position. Everyone that came to my STARC sessions knows this one, because like, bam, nice. Okay. Now what? I have Br2 FeBr3. What is that going to do? Bromine. Yeah, it's just bromination. It's going to add a bromine to my benzene ring. Is my benzene ring activated or deactivated right now? Deactivated, right? That double bond O next to it, that's a deactivator. So I'm adding a Br2, FeBr3. It's going to go, if it's a deactivator, is it going to go meta, ortho, para? Meta, right? Is electrophilic. So my meta position right here. And now I'm using SOCl2 and heat. That's a Orgo2 reagent. What does that do? Yep, it turns my OH on my carboxylic acid into a Cl. Otherwise, it turns my carboxylic acid into a acid chloride. So that's going to look like this. And then my last step is this CH3NH2. And what is that going to do? Exactly. It's going to turn into an amide. So it's going to substitute out the Cl now for an NH. So now we're just, you know, this is carboxylic acid derivative chapter. We're just messing with our carboxylic acid at this point. So our final product will have this NH2 with the CH3 on it. And it will still have this Br to the meta position. And And the only answer that gives you that is A. Yes, the double bond stays. Did I lose a double bond anywhere? Where? It's an amine. Yep.
Oh.
The double bond's there. It's just a carbonyl, but instead of the Cl, it was a carboxylic acid with an OH. Then we subs it for Cl. Then we substituted it for the primary amine, and now it's an amine. Okay, cool. So I have some more questions on spectroscopy or the nucleophilic aromatic substitution, or I have more synthesis problems. What do you guys want to do? Synthesis? Do we agree for synthesis? Yeah. We can maybe do some synthesis in spectroscopy or just synthesis, whatever you guys want to do.
I feel like synthesis has it all.
Yeah, synthesis does have a little bit of everything in it, so synthesis is a good one.
You can't add a deactivator, right?
Yeah, you can add a deactivator. So when you do nitration, you're adding a deactivator, right? You're adding an NO2, which is a deactivator. When you do acylation, you're also adding on to you're adding a deactivator, right? You're adding on that carbonyl. That's a deactivator.
So with acylation, you're adding to it.
Acylation, you're adding an activator because you're adding just a regular alkane.
And then acylation.
Acylation, you're adding a deactivator because you're adding a carbonyl, which is a deactivator. Does that make sense? You already have a deactivator, you can't do Friedel-Crafts. You can do other stuff. You can brominate it or you can nitrate it, but you can't do Friedel-Crafts. You can't do acylation or alkylation. Those are Friedel-Crafts. Okay.
If it has bromine,
you can, because bromine's weak. It doesn't. Oh, we did that question. Oh, this is a good one. So, which starting material would be best suited for the preparation of this labeled tertiary alcohol using carbon-13 labeling, methyl magnesium bromide? Okay, methyl magnesium bromide is just Grignards with a methyl on it. Okay, so don't let that confuse you. Carbon-13 labeling, that's something that you guys are like, what? It's something that they do when they're trying to figure out how a synthesis works, like all of those mechanisms and those arrow pushing that you guys see, like someone had to figure that out, right? So one thing that they do is they'll use carbon-13 acetope, and you can use, spectroscopy and all those methods, mostly mass spec, to see if you have, where your carbon-13 is. So they're using this carbon-13 to track what's happening in the reaction. So if you notice, you have a carbon-13 in your reagent, right? And we want 2 carbon-13s in our product. So it's asking which one of these is going to give you this product, not just that product, but that product with the right amount and right placement of carbon-13s. So this is pretty much like a mechanism problem. This one, when you use a Grignards on like a diester, what happens? I honestly don't even know. I've never seen it. It's like a trick question. I think that it would like eliminate one side and then do it again, and it would have like 1 billion carbon-13s on it if I had to guess. But I've never really seen that. I think that's like a trick-esque question. I would imagine that's what happens. But even if that is what happens, even if what I imagine happens, you would have 4 carbon-13s and 1 or 3. That doesn't make sense. You would have 3 carbon-13s, I guess, and an alcohol, and we only have 2, right? Because we would have 3 of these that added to it, and both of these would have left. So that can't be the answer. Over here, we already have a carbon-13 on it again, right? So that's going to be too many. Over here, we have this ketone that has 2 carbon-13s on it. If you add a carbon to a ketone, right? it's going to be the same thing where you have too many carbon 13s. It's going to give you the tertiary alcohol. This Grignard's is going to add right here, and this is going to go up. But now you're adding another carbon 13 to this. So now you should have 3 carbon 13s, and your answer only has 2, because you started off with 2 in your product, and then you added 1. So that's too many. For this problem, we have this ester as a good leaving group, and we start off with a regular carbon, right? It's not labeled as a carbon 13. When you have something with a good leaving group, how many times can Grignard's go? Twice. It can go twice, right? We can add to it once, and then our carbonyl can reestablish and push our ester off because it's a good leaving group. And now we have a carbonyl, now we have a ketone, right? With 1 carbon 13, we can add again, and then we have 2 carbon 13s and 1 regular carbon, so that's why this one is the right answer to get to this tertiary. You might not get a question just like that, but I think I remember in my exam getting one of these carbon 13 labeling questions. So I think it's just helpful to see it and see like what it's actually asking. That way it's not as like confusing when you get it on the exam. Does that make sense? Any questions on what they're asking or why that's the answer? Okay.
And then the Grignard won another time. Is that what happened?
Yeah, so at first, you want me to draw the mechanism? Wait, I'm sorry, it's 7:30. It's supposed to go 5:30, 7:30. Ha! I need to give you guys some evaluation forms. Don't leave. Oh, I didn't do a head count. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. There was like 3 guys there. 14, okay. I thought it was over at 7:45 for some reason. Okay. I was gonna keep going. You guys just gonna let me go. No problem. Here you go. Here you go. Yes.
Thank you.
Oh. Here you go. Yeah. Here, let me pop.